I want to go through some optimization problems today to go through the steps that we're going to use to set up, solve, and check some of our answers. And I want to start by just saying that these are all going to be different problems, and so they may require different tools. Sometimes we may need a picture. Sometimes we may need to do some experiments, think using common sense to figure out what the domain or range of these problems might be. But at the end, basically every problem we do is going to involve setting up a function that represents what we're trying to do. And so I'll try to maybe switch between paper and pencil and using Desmos to get some of the answers here. But I think it's best to just dive in with some examples. And I just Googled and I found this beautiful collection of calculus problems on a website at UC Davis. And these problems, if you just Google optimization problems UC Davis, they'll come right up. But these have full written solutions as well on the website. And so I'm happy to present some of these solutions because the solutions are already out there. And so let's just start with this first one. It says find two non-negative numbers whose sum is 9. And so the product of one number and the square of the other number is maximum. Well, what on earth is this even asking? Well, let's think about it. And so we have two non-negative numbers. We need to call them something. I don't know. Let's call them x and y. And so let's call the numbers x and y. And these are supposed to be non-negative numbers. And so these are non-negative numbers. And so non-negative means that x and y are both going to be greater than or equal to 0. Okay? So it's not quite the same as positive. It just means they can't be negative, so they could be 0 and bigger. And what we know about them, let's see what we use. So we know their sum is 9. So we're given x and y are greater than or equal to 0. And we know their sum is 9. So we know that x plus y equals 9. So I guess we can get rid of all this because we've now summarized it here. And then what we want to do, so I'm going to write this as a different line. I'm going to say that we want the product of one number and the square of the other number to be maximum. So we want blank to be maximum. I'll say maximal, or in other words, as big as possible. And what is it we want to be bigger? Well, we want the product of one number and the square of the other number to be as big as possible. So we want x times y squared, the first number times the square of the other number. We want that to be as big as possible. Okay. And so let's try to think about what's going on here, right? And so we can just kind of start with an example, right? What would happen if x were equal to 1? And then, well, I guess x plus y has to equal 9. So if x were 1, then y would have to be 8. Then that would mean that x times y squared would be 1 times 8 squared, which would be 64. So that's one possibility. But what would happen if, say, they were equal? What if they were, I don't want to deal with fractions. So let's say that one was 4 and the other was 5. Then, of course, they add up to 9. And now if we work out xy squared, that would be 4 times 25, and that would be 100. Right? So 25 there, of course, is just 5 squared. And you'll get 100. And so you see that, oh, wow, we got different numbers, right? And now the question is going to be, can we find numbers that might even be bigger than 100? Okay, for instance, what if we were to try something like x equals 0, y equals 9? Well, then x times y squared is, it's going to be 0. Right? And so depending on the numbers we put in, we're going to get different possible answers. And our task is going to be to figure out what we can do to get the biggest possible value of x times y squared. And so what I might recommend is just pause the video right now and explore with some numbers on your own to see how big you can get this x times y squared to be, and see what you think. All right, so I hope you paused the video. I hope you tried some numbers and maybe have a guess as to what may or may not work. You may also have a question, right? You may also be wondering, when I wrote down x times y squared, why didn't I write down y times x squared? It just says the product of one number and the square of the other number. And that's a good question. But because of the symmetry of this situation, if one number is 4 and the other number is 5, we just have the two numbers. And so I'll tell you what, we'll see that when we go further down the line. Right? So we've done our example. We've got some data. I'm going to kind of get rid of this because now we're ready to set up the problem. And our goal is to now use this relation that we have. So we have x plus y equals 9. And what I can do is I can say, well, hey, I know that whatever x and y are, they're related by this equation. So I know that y is going to be equal to 9 minus x. And so the function I'm trying to optimize is, I'll call it f of x. Well, I know it's going to be x times y squared. So I'm going to maybe write a y squared in here, but I'm going to erase it because I'm trying to make x times y squared as big as possible. But I know what y is. I know that y is 9 minus x. And so I know for a fact now that if I, no matter what x and y are, they're going to add up to 9. And so this is really the function that I'm trying to optimize. And so now I'm going to open Desmos. To open Desmos and see what we can see. So I'm going to graph this function and see what that looks like. So when I open Desmos, and I graph this function, which is f of x equals x times 9 minus x all squared. I have to zoom out a little bit so I can see everything. But I get this function here, and the scale's a little bit off. Maybe I can change the x values to go from 0 to 20 or something like that. But if I look at this function, I can see that it takes on lots of different values as I go through. And I can look and say, well, the biggest value looks to be right around here until I get further on in the graph. And so we're trying to find the maximum of this function. And you may be looking at it and thinking, well, why wouldn't I just keep going? Why wouldn't I let x equal something like 14 or 15, where the graph keeps getting taller and taller? But if you remember in our problem, what did we know? We knew that x and y were two numbers that added up to 9. And so that means that x and y, remember they were non-negative, so they're both greater than or equal to 0. So the range for those two numbers had to be between 0 and 9. We couldn't have one equal to 10 or 14, because that would mean the other number would have to be negative. And so really, if I want to graph this function as most accurately as I can, I would want to add in that restriction that, hey, my input x needs to be between 0 and 9. And so now when we look at it, I can see really from the graph that the biggest possible value is going to happen when x equals 3, and that y value, that output, is going to be 108. Okay. So let's go back to Desmos, or back to our writing, and see what happens. And so we have a guess from our graph. I'll do this as a little thought bubble out here, that I'm thinking that the answer is going to be a maximum at x equals 3. And the maximum value, then x is going to be 3, y must be 6, because remember the numbers have to add up to 9. And then xy squared is going to be equal to 108. So that's going to be our thought at what the answer is. But let's see what the calculus says. Let's see what we get by looking at equations. So I have this function, f of x equals x times 9 minus x squared. And I know to find the max of any function, on a closed interval, say the closed interval from a to b, what do I need to do? I need to check the endpoints, and I need to check what happens at critical values. So call them critical points, I think. So let's see how this is going to work. So in this case, what is our domain of our function? Well, we need two numbers that are greater than or equal to 0, and their sum has to be 9. And so really what that's saying is that really our domain, in this case, is going to be that x has to be between 0 and 9. Right? We can't have any number be bigger than 9. And so if I check those two endpoints, let's see what happens. So if I check x equals 0, f of 0 is going to be, if I plug in 0 for x, I'm going to get 0 times 9 squared, so that's 0. And if I plug in 9, that's the other endpoint, I'm going to get 9 times 9 minus 9. Well, 9 minus 9 is 0, and so I get another 0. And so my two endpoints, remember we saw that on the graph, right? Two endpoints on our graph were right here at 0. And so yeah, that's clearly not going to be a maximum. We're going to be able to get bigger numbers than 0 by some any other number, basically. And now what we're going to do is we want to find the critical points. So let's check some critical points. So how do we find critical points? So these are points where the derivative is either 0 or it's undefined. And so we're gonna work that out and see what we get. And so now would be a great time to pause the video and think about how you would find the derivative of this function. And you can think about, did you want to multiply it out first? Would you want to use the product rule? Which method would be your preferred method? So I'm going to do my method in 3, 2, 1. I'll just say that I'd be happy to just use the product rule on this, right? Because it's already in a product. I don't really want to FOIL anything out. And I think maybe if I FOIL things out later, maybe it won't be too bad. So I'm going to use the product rule. The derivative is going to be 1 times 9 minus x squared plus x times the derivative of the second factor. And now, what am I going to get for my derivative? Well, I use the chain rule. So I'm going to get 2 times 9 minus x times -1. Remember, I have to multiply by the derivative of the inside. What's the derivative of 9 minus x? It's -1. So just double check that if you have any questions. And so now when I write this down, I'm going to get 9 minus x all squared plus, let's see. So really, I get minus 2x times 9 minus x. And so this is my derivative. And I can keep going because I'm looking for points where it's 0 or undefined. And so if I'm going to set this equal to 0, it might make sense to factor. And so I notice a big old factor of 9 minus x. Right? You notice that this 9 minus x squared, I can split up as 9 minus x times 9 minus x. And then the other term is going to be minus 2x. Again, pause the video at every step here because these are algebra skills that are probably a little bit rusty. And just make sure you understand why, if we FOIL this out, we would literally get the same as the equation above it. And that's why we're using equals. And so now just a little bit more simplifying, 9 minus x times 9 minus, okay, I guess it's 9 minus 3x. And so now we have our formula for our derivative. And so now if I want to set this equal to 0, So now remember, I'm looking for points where my derivative was 0 or where it was undefined. And so if I were to set f prime of x equal to 0, what do I get? Well, I get 9 minus x times 9 minus 3x equals 0. And what are my two solutions that I get? I get 9 minus x equals 0, or 9 minus 3x equals 0. So this is going to give me x equals 9. And this one is going to give me x equals 3. So in both cases, I got nice whole number solutions. And now what we have to do is we can just kind of think about where these are going to go on the graph. So we've already checked that at 9, our y value is going to equal 0. Sorry, maybe I shouldn't. So if I plug in 9, sorry about this. If I plug in 9, I'm going to get a value of 0. So this is not going to be a maximum. And if I plug in 3, what am I going to get? Well, remember our original function. What was our original function? It was x times 9 minus x squared. So f of 3 is going to be 3 times 9 minus 3 squared, which is 3 times 36, which is 108. And so now what do we know about our function? Well, let's just try to draw a graph. I know we've seen one on Desmos. But now let's just think about what our function is doing. Right? We know at 0, our function is 0. We know at 9, our function is 0. And we know at the number 3, our function is equal to 108. And we know that our derivative, we know that our graph has to have slope 0 here. And so if you think about what could possibly happen, because this is a nice polynomial function, I mean, it has to go up until it gets here. And since it has slope 0, it has to just come back down. And so just kind of common sense is going to tell us that in order to get up there, it has to come back down. And so drawing a graph using a graphing calculator would be a way to kind of confirm what we've been doing. But if we want to kind of really, really solidify everything that we could do, we could use the first derivative test to really emphasize that this is going to give us a maximum. So first derivative test, we think about what our function is doing. Here's 0, here's 3, here's 9. Think about what's happening with our function. We know the derivative is 0 here. And if we test a point to the left of 3, well, let's imagine, remember, this is our formula for the derivative. Imagine we plugged in a point like 1 or 2, anything to the left of 3. Well, anything to the left of 3, well, this factor is definitely going to be positive. If we do like 9 minus 2, and so is this factor. And so we're going to be getting positive numbers in here. And similarly, if we test a point to the right of 3, like maybe a number like 5, then this factor is still going to be positive. This number will then be negative though, because if we let x equal 5, that will be negative. And so doing a test point over here, going to give us a negative number. And so what that tells us is that our function f of x must be increasing over here, and then it must be decreasing. So we get to 9, and that will verify that f of x is maximum at x equals 3. So a lot of algebra and kind of careful calculus went into this. But again, I'll just kind of summarize the steps that we had. We wrote down what we were given. We were given two numbers that added up to 9. They were both greater than or equal to 0. We wrote down a function that we wanted to optimize. And we wrote that function as a single variable. And so this is the function to optimize. to optimize as a function of one variable. And we then thought about a graph. We looked at the endpoints of the interval. We checked the critical points. We got a critical points of x equals 3, also x equals 9. And we checked those points and we found that among those, the largest possible value was equal to 3. Happened when x is equal to 3. And so, yeah, so this is the first of a series of videos I'm going to make about optimization problems. They can get kind of long, so I'm going to stop this video here and see you in the next one.